All right, welcome to day 4. Your homework, you have video 5-4. Today we'll be talking about mean value theorem and Rolle's theorem. Now, sometimes people get confused between the two, and it's important to make sure you're okay with each of the two theorems, because like on our next quiz, if you flip-flop the two, that's getting every single question wrong. So you want to make sure you're okay the difference between the two. So first, they each have some initial conditions. The mean value theorem, first we need to know that it is continuous on a closed interval AB. And it also needs to be differentiable on the open interval AB. So continuous, we mean there's no holes, jumps, asymptotes. Differentiable, no corner points, no kinks. If those things are true, then we know that our derivative at some point must equal our slope between the endpoints. Okay, so in both of them you're taking the derivative, but in mean value theorem you're setting the derivative equal to the slope. Now, a way I think it helps to remember that is mean value theorem starts with an m, and in math class we usually let m represent the slope. So that can remind you mean value theorem set it equal to the slope. In Rolle's theorem, our initial conditions, the first two are the same. We're continuous on the closed interval AB. We are differentiable on the open interval AB, just like before. And then the third one, f of a needs to equal f of b. So that means the y values of the endpoints. If those things are true, then we're guaranteed there's an f prime of c that is equal to 0. Now, a thing that helps me remember that is the second letter in Rolle's name is an O. O looks like a 0, so we're setting the derivative equal to 0. Now, in both theorems, we eventually need to find the y values of the endpoints. In Rolle's theorem, you need the y values of the endpoints to check and make sure they're the same. In mean value theorem, you need the y values of the endpoints so that you can actually do the slope. So in both cases, you should be finding the y values of the endpoints at some point. All right, so we're going to look at a few Rolle's theorem examples, and then we'll look at one mean value theorem example. So we want to verify that the function satisfies our 3 hypotheses for Rolle's theorem, and then find any number c that would satisfy the conclusion of the derivative equaling 0. So first hypothesis, it's got to be continuous on the closed interval AB. So we have a parabola here. Parabolas are continuous everywhere, so that's good. We need to be differentiable on the open interval AB. Well, parabolas don't have any corner points or kinks, so we're good on that too. And 3, we need to see, does f of a equal f of b? Well, let's test that out. Let's do f of 1 and f of 3. When we sub in 1, we'll get 5 minus 12 plus 3. That'll give us 8 minus 12, so we get negative 4. When we sub in 3, we'll get 5 minus 36. 3 squared is 9, times 3 is 27. So this will give us 32 minus 36. We also get negative 4. So that checks out. F of a is equal to f of b. So, because those things checked out, we are guaranteed our derivative should equal 0 somewhere on the interval. So let's take the derivative. We'll have negative 12 plus 6x. We'll set that derivative equal to 0. add the 12 over and divide by 6, so we get x equals 2. Now when you get an answer for both Rolle's theorem and mean value, make sure it is in the open interval that we want it. If it is not in the interval, then you know you did something wrong. I see lots of times on quizzes and tests, people will get their answer here, and it's not even in the interval, so that should have told them, oh, I made an error somewhere along the way, and I should check my work. Okay, 2 is in our interval from 1 to 3, and that's good. Rolle's theorem guaranteed we would get at least 1 point. Now, sometimes you'll get multiple values of x. Okay, still always check and see if it's in the interval. Sometimes some of them are in the interval, other ones are not. So you would only circle the ones in the interval as your answers. So same directions for this one. We're going to do Rolle's theorem. We want to see the initial conditions, make sure they're satisfied, and then we want to check and actually find the numbers when the derivative will equal to 0. So step 1, we want to know, is it continuous on the closed interval AB? Well, the negative 1/3 x part, that's linear. That's good everywhere. Radicals, we've got to make sure we don't have negatives under the radical. And on 0 to 9, there will be no negatives under the radical. So we're okay for continuous for those. And remember, we saw early in the year that most of our functions are continuous on their domains. Next, we want to see, is it differentiable on the open interval? Well, square root functions and line functions, they don't have corner points or kinks, so we're okay. And then lastly, we want to know, is f of a equal to f of b? So we can do that off to the side. If we sub in 0, we'll just get 0 in both spots. If we sub in 9, we're going to get 3 for the square root. 1/3 of 9 is also 3, so 3 minus 3 gives us 0. So that does check out, that f of a equals f of b. Now, usually using context clues in the question, you can often tell if it should be checking out or not. Okay, it said to verify them, so if you're not getting it to check out, then there's probably some error you did in your calculations. So Rolle's theorem now applies, so we're guaranteed our derivative is going to equal to 0 somewhere. So let's go ahead and find that derivative. We'll have 1/2 x to the minus 1/2 and minus 1/3. We'll set that derivative equal to 0. And in doing that, remember when we actually work with things, it's better to work without negative exponents. So let's bring that down to the denominator, because it's the negative exponent. We can add that 1/3 over. We can cross multiply. We can divide by 2. And then we can square both sides, and we'll get x equals 9/4. We shouldn't just move on to the next question. We want to check and make sure that's in the interval. 9/4 is 2 1/4. Okay, 2.25 is on 0, 9. So then we're probably in good shape. So that's the spot where basically the graph turns back around and heads back to the original y value. That's what creates that y, or that derivative value of 0. It leaves a y value, has to come back to it, so it should turn around at some point. That's why Rolle's theorem guarantees that there should be one spot the derivative is 0. All right, so in this one, we've got our function, 1 minus x to the 2/3. First step, we want to show that f of negative 1 is equal to f of 1. So f of negative 1 raising to the 2/3, that's cubed root and then squaring. When you take a cubed root of a negative 1, you get negative 1. When you square it, you get positive 1. So we'll have 1 minus 1, which is 0. When we put in 1, anything raised to the, or 1 raised to anything, I should say, is just 1. So we get 1 minus 1, so we again get 0. Okay, so we showed that f of negative 1 is equal to f of 1. But even though that's true, they want us to show there's no number in the open interval where the derivative is equal to 0. So let's do that. So let's take our derivative. We'll have negative 2/3 x to the minus 1/3. Okay, 1's derivative was 0 because it's a constant. We'll set this equal to 0, and we'll rewrite it without a negative exponent. So this is negative 2 over 3 cubed root of x. Now, a fraction is 0 when the numerator is 0. That's something we first talked about last week. Well, in our numerator, we have negative 2. There is no way for our numerator to be 0. So therefore, this derivative will never equal 0. But you might say, well, does that contradict Rolle's theorem? Through context clues, okay, this is telling us, well, maybe we shouldn't have used Rolle's theorem to begin with. Okay, we should not be using Rolle's theorem ever unless we've checked our 3 initial conditions. We only checked condition 3. Okay, we showed that f of a was equal to f of b. So we need to check our other initial conditions. Well, is it continuous on the closed interval? Well, that's a cubed root and then squared. Okay, cubed roots, you can have positives, negatives under there. Doesn't matter. So this is continuous. But differentiable, if we look at the derivative here, when 0 is put in for x, we get a 0 in the denominator of our derivative, meaning the derivative is undefined. It doesn't exist at x equals 0, which is on our interval. So differentiable on the open interval from negative 1 to 1? No, because it is not differentiable at 0. So therefore, Rolle's theorem did not apply. So Rolle's theorem did not apply since f of x is not differentiable on the open interval AB. Now, just from clues in the problem saying why does this not contradict, that should tell you, okay, we probably shouldn't be using Rolle's theorem to begin with. So check those initial conditions. All right, hopefully we feel pretty comfortable with Rolle's theorem. We're going to try a mean value theorem problem now. So similar to the Rolle's directions, we're going to verify that the initial hypotheses check out, and then we'll find any numbers that satisfy the mean value theorem. Mean value theorem, remember, has got the m, so we're setting the derivative equal to the slope between the endpoints. So let's first check and make sure it is continuous on the closed interval. It's a parabola. Parabolas are continuous everywhere, so that's good. Second, we need to make sure it is differentiable on the open interval AB. Well, parabolas do not have any corner points, kinks, so we're good there. Well, one thing I forgot to mention on the previous problem, if you had graphed 1 minus x to the 2/3, you would have seen a corner point at x equals 0. So that could have visually told you that the derivative did not exist at x equals 0. Now, the issue for us is you're not going to have a graphing calculator on your quizzes, so that's why looking at the derivative and seeing that x being 0 in the denominator would make it not differentiable is how you would go about doing it when you don't have a graphing calculator. All right, so back to this one. Our initial conditions checked out, so we need to now set our derivative equal to the slope between the endpoints. Well, we need to know what are our endpoints. We have -1 comma something and 1 comma something. So let's see what we get back for those. We'll start with the easier one, 1. When you sub in 1, you get back 3, 2, and 5, or in other words, 10. When you sub in -1, we get back 3, -2, and 5, or in other words, 6. So we'll do our slope. We got 10 minus 6 over 1 minus the -1, which will give us 4 over 2, which is just 2. That is what we will set the derivative equal to. So derivative would be 6x plus 2. We'll set that derivative equal to the slope between the endpoints. And what this is really saying, the meaning of this, is that our average rate of change, the 2 on the left, must be equal to our instantaneous rate of change on the right. And can't remember if I mentioned this in the video last night, but the mean value theorem actually could allow them to send you a ticket when driving on the thruway if the timestamp on your Easy Pass would show that your average speed is over 65 miles per hour. Because let's say your timestamp from Easy Pass when you went through the toll booth showed that you were traveling on average 67 miles per hour on the thruway. The mean value theorem guarantees that there must have been an instant that you were traveling 67 miles per hour at some point on your trip, therefore guaranteeing that you were speeding at some point. Now, they probably would never do that. It would be a political nightmare, but they would be justified in sending you a speeding ticket if your timestamp showed that your average speed was above the speed limit. So back to this problem, if we solve for x now, divide by 6, and we get x equals 0. Remember, always check and make sure it's in the interval. 0 is in the interval, so therefore that is our value of c. C is an x value that satisfies the mean value theorem. So that x equals 0, the line, or the tangent line, will be parallel essentially to the line connecting the two endpoints. All right, so that's it for the video. You can do one of two things if there's time left in the period. You can either start watching tonight's homework video, or if you want to grab a textbook, you can start working on the next problem set as well.